Okay, so welcome to our fourth or fifth research project. I'm not sure which one. Today we'll be talking about KFI matrices. So KFI matrices come from a field. They don't come from a field of signal processing, but they're inspired by a field of signal processing. So first I gotta talk about something called a Kalhman filter. Now, what is a Kalhman filter? It is a filter or an algorithm filter used in signal processing to reduce the SNR or signal to noise ratio of received signals. Received or perturbed signals. Okay, so this is a Kalhman filter, and what we're going to do is we're going to introduce some more topics. So we're going to talk about moving averages. And what I want you to understand is that given a graph that looks like this, say our stochastic process or any given share price. Right. So the moving day average, let's say, comes in a couple different flavors. Okay. So you have the 30-day moving average, you have the 60-day moving average, and you have the 90-day moving average. Okay. So each of these graphs, red I'm going to use for 30 days, so it's going to try to smoothly follow the graph. In some cases it overlaps, in some cases it doesn't, and this is what it is. It's at least it's continuous, but at least it's more well behaved than our original stochastic process. Now, secondly, we will be considering the 60-day moving average. So, on 60-day moving average, we will have a much more looser. It's going to correlate more weakly compared to our original moving graph. So, because it's done over the 60-day period, it's going to fail to detect smaller dips like this. And it's going to follow even weakly than a 30-day average. And lastly, we have the 90-day average. So we have the 90-day average that is extremely weak. It takes a lot of time for it to catch up to any given trend change, and so on and so forth. Okay. So now I've given you basically three colors, right? And seemingly no reason to consider them, right? So the moving day average is used to make decisions, wherein if I have a stock graph that looks like this, and I have a moving price that looks like this, these 2 points are really distinct. So at this point, I may either make a sell decision or a buy decision. At this point, I may either make a buy decision or a sell decision. It depends on, it's more complicated than simply deciding to sell and buy at a top or a lower intersection. However, it is useful in the sense that we use these as a tool to make our decisions. Right? So similarly, if we have other moving averages like this, then their intersection points are also objects of interest or concepts of interest. So now the Kalhman filter is much stronger than anything over here. The Kalhman filter almost very smoothly follows the graph, so you can barely see where I'm drawing it because of how close it is, and because of the port charts are colored, they don't have purple. And so this over here, this is the Kalhman filter. Okay. Now, the Kalhman filter is the best smooth approximator of your stochastic process, mainly because of this point. It is literally designed in or constructed as an algorithm purely to reduce the signal to noise ratio. Let me just write that up here. Signal to noise ratio is equal to your SNR. Now, like I said, these points of intersections are really important for us to make our decisions, right? So essentially, when we consider this graph over here, we are interested in all these points. Let me highlight them in yellow now. And I'm going to highlight them in yellow regardless of which 2 points are intersecting. Okay? So it's possible for the Kalhman and the original graph to intersect over here, 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 here. I might miss a few, but my point is that these are all the points of interest. Right. So you can see the Kalhman filter has frequent intersections with the original graph. Now let's consider the other moving averages. So all the moving averages are going to denote with okay. So for the moving averages, we have this point over here, 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 we have this point, we have more points like this, we have these points over here, these points over here, and that's about it, right? So clearly you can see that the moving averages are much less frequent than our Kalhman. And so, what do? We study each of these graphs. So, how do we detect an intersection? And how do we detect which graph is above and which graph is below? So we want to make that distinction. Now I'm going to draw some more diagrams. So if I have a graph that looks like this, and I have some smooth approximator that looks like this, okay? Now let's consider 2 different kinds of points of interest. We have this one and this one. Now for me to know whether the bottom function is above or below my original function, I have to see the slope at this function, right? So this is going to be the slope. And I have to compare this slope to the slope of this line segment where it intersects against. So let's say this is slope MA, this is slope original, and therefore in this case, for it to be below, my slope, my MA slope, has to be lesser than my original. Right? Now similarly, in this case, my slope of the MA is bigger than my slope of the original. Please note that even though this is inclined much more than this graph, this inclination is negative, okay? Just to avoid that point of confusion. And this inclination of the moving average is still positive. That's why the moving average is greater than the original, right? Now, using this sort of classification, we have 2 different kinds of intersections, right? So, basically, what we do is we form a matrix. Yeah, so now we define the KFI matrix. The KFI matrix stands for Kalhman filter intersection matrix. And it is a matrix based depending on time t, and it is as follows. So we have one column for 30-day, we have one column for a 90-day moving average, or no, yeah, we have 90-day moving average, we have our 60-day moving average, we have our 30-day moving average, and then we have our Kalhman filter. And then we have the original graph, or we may or may not consider the original. Now we have 90 over here, 60, 30, and KF. And now when my Kalhman filter intersects with 30-day moving average, I have two possibilities. I may either note it over here at this intersection, or at this row and column, or I may note it here in this row and column. And so how do I decide? So this is the first, second, third, and fourth, and this is also the first, second, third, and fourth. Then this point is the point Mij, which is given by M3, and this point is given by the point M3, right? So it will be Ij or I rho J. Okay. Now, so for a given function in the ith row and jth column, do I go to Mij or Mji? Or do I go to M34 or M4? Okay. This is the question, and this is how we decide. So, if I crosses J such that slope of I is greater than slope of J, similarly, if J crosses I such that slope of I is less than slope of J, then we assign Mji is equal to, or we may even change it such that Mji has Mji is equal to 1. And another note over here, Mji in this case, there is an additional condition. So if I doesn't intersect J, then J is equal to 0. No, I can't intersect itself. Hence, Mii is always equal to 0 for all I. Now, the last condition is Mij is antisymmetric, that is, it is equal to minus Mji. Okay, cool. And now we're going to talk about what research areas are in. So, research interests, research okay. So, we are interested in our decision-making process, and for our decision process, we require information about either the invertibility of our matrix, the determinant, right, what else? We also can and similarly, we also care about converting our matrix, and we pretend that this is an adjacency matrix of some probably a direct approach. And we want to use this idea to take our matrix and convert it into a graph. Now, given this graph, we want to find the moduli space of our graph. If it even makes sense to talk about the moduli space. If it doesn't make sense to talk about moduli space, then just having a graph space would be more than enough to talk about how close two graphs G1 and G2 are similar to each other. And that concludes our interests in this area. Thank you for watching.